Hey, sixth grade, welcome to your flipped lesson on lesson two, Earth's interior. So I thought I might just start this video. I found a nice quiet place. It happens when one kid goes to college. There's an empty room in the house. I thought I'd come here so we wouldn't have to hear my dog barking, and she followed me upstairs. So I thought maybe I would introduce you to Lucy. Hey, Lucy. That's Lucy. That's the barking dog you see all the time. Yes, apparently she wants to just come and say hi. But okay, back to it. You'll be complaining that it's longer than 10 minutes. So we're going to talk about the structure of the Earth, but let's start by first figuring out how scientists know what the structure of the Earth is. How do they know about parts of the Earth that they can't see? Well, there are two types of evidence. And we say evidence is just information that supports what scientists believe makes up the interior of the Earth. So there's direct evidence. This one's pretty straightforward. Direct evidence is something you can actually see and test directly. So scientists get this from drilling. In fact, somewhere, I believe in Russia, they drilled a hole about 12 kilometers into the Earth, which is, goodness, like 9 miles. There's a story that they got so deep into the Earth, the heat and the pressure were too great that they did not have a drill at the time that could drill any further than that. But what they did is they took up samples from this depth, and they can observe the composition of the rocks at different levels as they were descending. So it does give scientists, while not a complete picture, it did give them some idea of rocks that were beneath the surface. Real direct way is through volcanoes, because volcanoes bring up lava. That is magma that is in the mantle, comes to the surface, and when it comes to the surface, scientists can study the rocks and minerals, or mainly the mineral content of the magma that comes to the surface. With technology these days, we also have lasers that can actually squeeze rock in laboratories under such intense pressure that they can replicate some of the pressures that exist deep inside the Earth. So direct evidence, drilling, observing lava, and then in-lab experiments with lasers. So indirect evidence. So this would be maybe something that you can't necessarily see, so you don't know exactly what the mantle and the core look like, but you can study indirectly. So indirectly, we study seismic waves. And seismic waves are waves produced by earthquakes. So when there is an earthquake, it produces a couple of different types of waves. The two that we'll talk about in earth science are P waves and S waves. These waves travel not just on the surface of the Earth, they travel through the entire planet. And these waves behave differently when they're traveling through solids versus liquids. Your book gives a really good example of just waves on the ocean that are coming up onto an island, how they propagate around the island. Well, seismic waves traveling through the Earth behave differently as they're moving through solid rock, liquid outer core, solid core, and so we can make some assumptions about what the interior of the Earth looks like by studying how these waves move. So let's talk about what it's like down there. Okay, so I guess let's start with the 3 layers. Okay, so we've got 3 layers of the Earth. I think you're pretty familiar with these. We've got our, hang on, let me move this out of the way a little bit. Excellent. We've got our crust, we've got our mantle, and we've got our core. And these layers, why they're layers, why it's not all one thing, is because they vary in composition, so what they're made of, they vary in temperature, and they vary in pressure. And so just an overview of temperature and pressure. Pressure is how much force is pushing down on a specific area. Okay? So as you descend deeper into the Earth, the pressure increases. This is pretty intuitive. As you go down deeper into the Earth, the entire crust is upon you. And the deeper you go down, then you have crust and part of the mantle. And the deeper you go down, you have crust, mantle, and outer core. So think of it as how much force is pushing down on top of you. If you are on the surface, you are just dealing with the force of the atmosphere, which, believe it or not, is quite a bit. But as you descend, you're dealing with the force of all of those layers of rock. So as you go deeper down, the pressure increases. Of course, as you go deeper down, the temperature also increases. For about every 40 meters of depth, your temperature goes up about 1 degree Celsius. So this sort of temperature decrease or sorry, temperature increase continues until you get down into your outer core, where it still increases, just only slightly less. So how does this happen? That's always the big question. So why and how does temperature increase, or where does that temperature come from, and why is it all contained in there? Well, I would say that there is intense pressure, and one of the main reasons it's hot is that intense pressure is creating a release of radioactive elements from those rocks, and those rocks then heat up. Those radioactive elements heat up the rock. Also, we'll talk about what what the situation was like when the planet was forming. And 4.6 billion years ago when our planet formed, there was intense heat from an exploding star. And some of that heat got trapped when our crust hardened. So if you have that question, it's a good one. And as we move through Earth science, we'll talk more and more about not what the structure is, but also how the structure came to be. I'm going to apologize in advance. This might be longer than 10 minutes. I'll have to give you a candy or something when you come to class. Okay, let's start with the crust. The crust is the outermost layer. It's also the thinnest layer. The crust includes all of the continents, but then also the ocean floor. There are two different types of crust. There's oceanic crust, which makes up all of the ocean floor, and there's continental crust. While they're all crust, they are made up of different things, different elements. So granite and basalt are the two rocks that we sort of compare when we're talking about oceanic crust and continental crust. Basalt makes up most of the rock on the ocean floor. It is darker colored, and it contains silicon and oxygen, but in general maybe a little more magnesium gives it this darker color, as opposed to granite, which is lighter, makes up mostly silicon and oxygen, that makes most of the continental crust. When I say the crust is thick, but not the thickest, it can be anywhere from 5 kilometers, which is 3 miles, to 40 kilometers thick. And in fact, under some mountains, it can be as deep as 80 kilometers, yet on the ocean floor, it would be its thinnest. So we'll talk a lot about the crust when we're talking about plate tectonics, but for the most part, just understanding it's the outermost layer. It's made up of mostly silicon and oxygen, which are the lightest elements, which means when the Earth formed, these elements rose to the top. Oh my gosh, my dog, Lucy, what you doing, huh? Yes. So these rocks mostly settled on the top. The heavier ones fell down, and they make up the ocean floor. It's important to note that both granite and basalt are volcanic rocks as well. Most of the Earth's crust is made up of igneous rocks from volcanoes. So we'll talk a little bit more about these types of rocks tomorrow and look at some of them. Next is the mantle. The mantle is a layer of hot rock. It is the thickest layer. It is made up mostly of magnesium and iron. So if we look on, and we'll look on our periodic table, these are heavier elements. So when the planet was forming, these elements settled down, and they were too heavy to make up the crust, and so they settled into making up the mantle. This layer is so thick that composition, temperature and pressure change as we move through it. So it's actually made up of 3 separate layers. It's like 3 layers within a layer. So the lithosphere, oh, hang on, my dog needs to get outside. There you go, Lucy. Okay, sorry about that. So these 3 layers are all part of this giant layer of the mantle, okay? So the mantle is about 3,000 kilometers thick. So you could sort of see how things would change if you were at the top of this layer versus being at the bottom. Your composition and temperature would change over the course of 3,000 kilometers. The uppermost layer is the lithosphere. It is rigid, just rigid, hot rock. Actually, the lithosphere contains a little bit of a layer of the crust and the uppermost portion of the mantle. The lithosphere is where sort of our plates, our continental plates, rest upon, and it averages about 100 kilometers thick. We say it is rigid because it is very much like the looks and sort of feels like, in terms of how hard it is, looks a lot like the crust. Okay. The asthenosphere, fun lab this week with the asthenosphere. We call this the plastic layer because although it is solid rock, it is bendable. It's flexible. So it's under a lot of pressure, but it is a rock that bends. This week we're going to do a lab, Oobleck lab. Oobleck is awesome, and it really does behave a lot like the asthenosphere. When we have a lot of pressure, like the asthenosphere has entire continents on top of it, that's intense pressure. It keeps that rock hot, and it keeps that rock solid. When you release that pressure through cracks in the earth or volcanoes, what happens is that solid rock becomes a liquid. That solid magma then becomes lava. And we'll talk a lot about how Oobleck is a really good representation of that. We call it a plastic layer because it is hard but flexible. It's kind of hard to imagine a rock being that way, but it gives you kind of an idea of how just much pressure is on that. And then we have a mesosphere. The mesosphere is right, it's like the lowest level, right up against the outer core. It is more rigid, meaning more like the lithosphere than the asthenosphere, and that is due to just intense pressure just holding that rock in place. Okay? Finally, we have our core. Now our core, again, if we're thinking about our periodic table, our core is made up of mostly iron and nickel, which are heavier than the others. And where we have the core, this is the most heat and the most pressure. Okay, we are at our deepest point, so we're dealing with the 3,000 kilometer thick mantle, and then the 80 kilometer thick crust pressing down on this core. There are two parts to the core. There's the outer core, which is liquid metal, and the inner core, which is a solid metal core. We're going to talk in class about the importance of the outer core and this liquid metal. This liquid metal moves, and since it's iron, it is magnetic, and it creates something called the magnetosphere, and we're going to talk about how that protects our planet in class tomorrow. So, sorry I went a little bit over. Your job tonight is to think about this lesson and answer some of those note questions that I gave you. And this week we have 2 lab activities that will help support a lot of the information in this lesson. So thank you. I was happy to introduce you to Lucy, and I'll see you tomorrow.